Hi, my name is Neha. I'm a junior chem major, and I've been peer mentoring for a year now. Started off with Chem 102, and I'm currently mentoring Chem 262. I hope to continue peer mentoring because it's been a really rewarding experience, I feel like, on both sides. I see that me being there in lectures really helps students clear up any misunderstandings, or if they miss something, they get to hear a different explanation. And it's been really rewarding for me as well because it's helping me to better teach chemistry, because understanding it doesn't necessarily mean that you're good at explaining it. And through peer mentoring, I've trial and errored how to actually explain chemistry and have noticed that I've gotten a lot better at it, and I hope to continue passing this knowledge that has been passed down to me and pass down my tips and tricks that I've learned throughout taking the courses. One study tip I recommend to students all the time, no matter the chem course, is practice, because chemistry is about applying concepts, and practice is the only way you can really understand the concepts well enough to apply them. You expose yourself to a bunch of different situations, and that really helps with applying. The course I hope to peer mentor is Chem 262, so I've chosen a problem from that course. And specifically, I've chosen a synthesis problem because this is easily one of the most difficult topics in organic chemistry, and having a systematic way of solving it really helps make it better and less scary. So the first thing I do is synthesis and see what's conserved between the reactants and the products. For this example, we can see that it's the benzene ring. And then the products, two substituents are added on to this benzene ring. So we think EAS because we have an aromatic ring and we have substituents added onto it. And with EAS, it's really important to see the relationship between the substituents. And between these two substituents, we know that they are meta to each other. This is important because the substituents, as is how they are on the product right now, neither of them are meta directors. So this should clue us into thinking, okay, one of these substituents was probably a meta director at first, the other one was added on, and then the original one was converted to its final form. It's likely not the chlorine because if we're thinking EAS, halogenation, it's added in one step, so it's not going to be a meta director first and then convert into chlorine. Chlorine just gets directly added. So we're focusing on this substituent right here then. So how is this formed from a meta director? So biggest thing is looking at the double bond, because there's very few ways double bonds are formed from the reactions we know in Orgo 2. And the biggest thing that comes to mind is Wittig reaction. So for this, we need a ketone or aldehyde, and we need a phosphonium ylide. So we would need something like this. To get the double bond in the right spot and in the product. And this checks off all our boxes. The ketone is an electron withdrawing group. It's a meta director. So if we had that, we could add the chlorine meta. So that's great. We have the last step in our synthesis. So now let's kind of work forwards. We worked backwards. Now let's try to get to that point. So how do we get a ketone substituent added on to a benzene ring? So we're thinking EAS, and a way to add a ketone through EAS is Friedel-Crafts acylation, where you have an acid chloride, AlCl3. And the acid chloride would have the same number of carbons, so it would look like this. And then we have AlCl3, and then we have an H2O workup. Do not forget the workup that is needed to remove the complex. So this allows us to add a ketone with the same number of carbons onto the benzene ring. There we go. And now we have the meta director needed to add the chlorine meta. So we do this through another EAS reaction. This is halogenation. you would get this intermediate. And now the final step is something we already talked about, turning this ketone into having a double bond. And this is the Wittig reaction that we discussed before, and we already have the reagent selected for it. And now the synthesis is complete. So there you can see how we broke down this complex synthesis into a series of steps, working backwards at first and then seeing what we need to get to that point. And it's really a lot more clearer than it was at first.